So let's just see how we're doing here with this. So we got a heavy box. We know its mass is 35 kilograms. It says it's being pushed up a hill by a force of 150 newtons over a distance of 20 meters. So a couple ways to go about this. Sometimes when I've got one that's a little more like involved, I'll just draw a picture of it for my givens. If that works better for you, go right ahead. Okay, givens are givens. Whatever way is most useful for you, go for it. Okay, so if I'm doing this, I'm just going to draw a picture of that hill. It's kind of steep, but okay. And I'm going to write that hill is 25 meters long. The question wants to know how much higher above the bottom would it be. I'd say that's probably my final height that they're looking for, okay, given the context of that question. All right, I got the box on there. It's going from the bottom to the top. There's 150 newtons worth of force pushing it, okay, and that is all I know. They don't mention any change in speed, so is it okay to assume it's not accelerating? Yeah, they would have to mention that, and they don't, so we can assume it's not accelerating. All right, so I've got those things there, okay. What kind of energy is being changed? Potential. How do I even know work is being done?
Because you see that there's force over a distance.
Right, there's a force and a distance as a given, usually a dead giveaway. Okay, but also, can I just see from the context of this question that it's going to have more energy after than before? Okay, both are signs that work is going on. The reason I bring that up is the next thing we talk about mathematically looks very similar, but is a situation where no work is being done. But you're going to get similar givens. So it's important to be able to tell when you read a question, work's being done in this one versus the next kind we're going to talk about being able to tell no work is being done in those. Okay? All right, so in this one here, we've got work equals a change in potential energy. So we've just done the first two steps. We wrote out our givens, we decided what kind of energy was changing. Okay, we were told force and distance, so we're going to substitute that for W. Okay, and we're going to go final potential minus initial potential. Okay, did I get done a favor in this one? What's my initial potential? 0. I don't have any potential energy at the bottom of a hill. Okay, so I've got that. That's going to mean then that force times distance equals m times g times h final. How do I get h final by itself?
Divide by m.
Divide both sides by m times g. Okay, and so when I do that, I am going to have 150 newtons times 25 meters divided by, it was 35 kilograms, right? Yeah. Okay, 35 kilograms times acceleration due to gravity 9.81. Okay, so 150 times 25, okay, divided by 35 times 9.81. All right, so we are looking at 10.92 meters as the final height. Okay, for that. Everybody all right with that? How are you feeling about these kind of questions? Okay, are we starting to get the pattern? Let's try one here that's different. Okay, try this one. All right, so you got a car applying its brakes, so it's traveling along. Okay, it's going 20 meters per second. Okay, it applies the brakes. 10,000 newtons worth of frictional stopping force is applied. Okay, it slows from 20 to 6. Car's mass is 1,700 kilograms. Okay, we're looking for how far it traveled. Okay. For how many of you, when you do this, are you getting negative 30.9 when you do it? Okay, it's okay if you are. We haven't really talked about this property of work. Work, while scalar, can be positive or negative. Does that seem contradictory? Okay, and it's okay if it does. Here's why it's not contradictory. It's not about what direction the work is being done in. It's about whether the work represents a gain or a loss of energy. Okay? Negative work means you are transferring mechanical energy to something else. You are losing mechanical energy. In this example, is the car losing mechanical energy? It is, because it's going slower, right? Okay? It has more mechanical in the form of kinetic at 20 than it has at 6 meters per second. that energy has to go somewhere. From the car's point of view, that's a loss. It's negative work. It did that on something else. Okay? So, here's the thing we have to realize. Braking force produces a positive or negative acceleration? Negative. Well, acceleration is vector, so is force. Okay? Braking force is negative 10,000 newtons. That way, you'll have negative 10,000 newtons, okay? And when you do the other side of the equation and you go final, which is smaller, minus initial, which is bigger, and you get a negative on the other side, when you do everything, it ends up working out. You got a negative divided by a negative, and you'll get a positive number, okay? So we'll show you here what's going on. All right, so obviously in this one, work is being done, okay? And it's changing the kinetic energy. Kinetic energy of the car. All right. So we've got our force, okay, distance, and we're going EK final, which is small, minus EK initial, which is bigger. All right. And in this case, we don't have an energy that's zero, do we? Okay. So that's a little bit different, right? We've had a whole bunch of questions where the initial was zero. In this case, it's not. All right. So. I'm trying to figure out how far the car travels. What am I looking for? Distance. So I got to move force over to the other side, right? All right, and we just finished saying force is negative. So when I do this operation, EKF minus EKI, I get a negative number. But that's okay. I'm going to divide by a negative number, and a negative divided by a negative is? Positive. Because I can't say that my distance, which is a scalar quantity, is a negative number. Agreed? Okay, and that's what we're calculating. We're not calculating displacement with this formula, we're calculating distance. The other side of that would be applying the brakes doesn't make you go backwards. That would be really dangerous. Okay? They make you accelerate backwards, but they don't make you go backwards. Eventually you stop and then you have no kinetic energy anymore. Okay? So we are going to divide both sides by force. Okay? Bring it over here. So that's going to give us 1/2 times mass times final speed squared minus 1/2 times mass times initial speed squared divided by force. Okay, everyone all right with that idea? When I plug in my numbers, okay, we're going to have 1/2 times 1,700 kilograms, the mass of the car, okay, times 6 squared, because it's slowed down, final is smaller, 1/2 times 1,700 times 20 squared, divided by negative 10,000 newtons. All right, so when we plug all that in, 0.5 times 1,700 times 36 minus 0.5 times 1,700 okay, times 20 squared, which is 400. All right, so they got negative number. All right, now I'm going to divide that by negative 10,000 newtons. Okay. 30.94 meters. Okay. If you did this question and you were just going through it, just didn't realize the force should be negative, and you got a negative number for distance, you would all know to go, hey, wait a minute, that can't be negative, and just not write it, right? Okay. Because that's going to happen probably somewhere. All right. Is that making sense to everybody? Okay. I think maybe one or two more here. And then we'll, did we do that one yesterday? I feel like we did the slingshot one yesterday, right? I think so, yeah. That one we didn't do. Okay, let's try that one. Pretty similar to the one we just did, but it does have one small trick in it. Okay, and then we'll probably start talking about conservation of energy after that. All right, so if we're having a look at this, guys, our givens are, okay, that we're told how far the spring is compressed. That would be our distance. Okay, so 0.23 meters. Our mass is 0.650 kilograms. Okay, and our initial speed is 1.2. Oh no! You gotta be kidding me. Oh, there we go. Okay. All right. Our initial speed. Come on. I don't like you. Okay, here we go. Okay, VI is 1.2 meters per second, okay, and VF is 3.1 meters per second. All right, in this question, is work being done? Okay, and what kind of energy is changing? Kinetic, okay. All right, so we got a change in kinetic energy. Okay, we've got force times distance equals 1/2 mvf squared minus 1/2 mvi squared. And we're looking for the force. So what do I have to do with the distance? Divide it over to the other side. All right, so when we're plugging in our numbers here, we got 1/2 times 0.65 times 3.1 squared minus 1/2 times 0.65 times 1.2 squared. And divide all that by 0.23 meters. So 5 times 0.65 times 3.1 squared minus 0.5 times 0.65 times 1.2 squared. And divide that by 0.23. All right, so that's going to require 11.54 newtons worth of force. Okay, everyone all right with that? Okay. How are we feeling about these? Okay, do we want to do some more of this or do we want to move on? How many people would like to do a few more work energy theorem? Okay. We'll probably still come back to this a little bit now and again for the remainder of the unit, okay? But we can start talking about the law of conservation of energy here a little bit. All right, I'll give you guys about a 3 or 4 minute break here while I clean things up on the board, and then we'll get into law of conservation of energy. Okay, so we've been talking about work energy theorem. In work energy theorem, okay, clearly, because it says right in the formula, mechanical energy changes, okay? Because that's what work is. If you do work, you are going to change the mechanical energy of an object. So let's say you've got like a cliff, all right? And on the other side of this cliff is like a path, okay, that you walk up. So let's say that you've walked up this path and you've carried a box up there with you. Have you done work?
Yes.
Okay, so the box now has energy, would you agree? Okay, it's all potential, but it has it, right? Okay, so you do this work, you give energy to the box. Then you throw the box off the cliff. Okay? Does the box still have the same amount of mechanical energy here and here? What do you think? And I don't mean after it hits the ground and is destroyed. I mean the instant it hits the ground. Yes. Okay? You have given that box energy. According to the law of conservation of mechanical energy, the only way the energy of that box can change is if it does work on something else. Okay? So while that box is falling, its mechanical energy remains the same. How is that possible? At the top, it's all potential. What is it at the bottom? It's all kinetic. So how is it possible for it to have the same amount of mechanical energy all the way to the bottom?
Well, when it's at the top, it has the same amount of potential energy that it would if it was falling. As Kinetic energy is the response.
So, okay, so its potential here equals its kinetic here?
Yes.
Yes. Okay, that's true. Because how do we calculate mechanical energy?
Potential plus kinetic.
Right. Okay. To calculate mechanical energy, we take the potential energy of an object, add it to the object's kinetic energy, and that gives us our mechanical energy. Okay? So the same would be true here. Okay? It's just at the top of the cliff, it only has potential. Okay? It doesn't have any kinetic because it isn't moving yet. And on the ground, its height would be 0, so it wouldn't have any of this. So we're not saying anything that isn't true. We're still saying that the mechanical energy of the box doesn't change. What does change is how much of it is kinetic and how much of it is potential. Okay? If you recall, when we started talking about energy, I told you potential energy can't do any work. It's the potential to do work, but potential energy in and of itself doesn't do work. Kinetic energy does. So as this thing falls, right, its kinetic energy goes up, its potential energy goes down, and its ability to do work goes up. I mean, potential energy is also the ability to do work. It just doesn't actually do any until it's converted to kinetic, which is exactly what happens when an object falls. Okay? Everybody with me there? Okay. All kinds of things depend on this, or lots of things actually use this concept in order to work. Okay? The other day when I was at the PD day, this is the thing I accomplished that was good. Okay? Oh, again? So, I'm going to show you this thing I was working on the other day, okay? And it has to do with a problem that was faced back in the early days of the Cold War by nuclear weapon carrying bombers, okay? The big concern back in that day was that we didn't have any stealth technology, so you couldn't just fly over something with impunity and not worry about it, okay? So planes had to fly really low to the ground to be under the radar, which is fine, you don't get detected by radar. But you also can't drop a thermonuclear weapon when you are less than 100 feet above the ground because you'll be consumed by the detonation, okay? So there was this, kind of serious problem that they had with this part of their, let's say, war games, okay? So someone devised this scary but ingenious way to overcome them. The plane would fly in really, really low to the ground. Okay? And then it would actually fly over its target. And then it would pull into a steep climb. And it would actually do a roll. Okay? So it would go up, 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 and then it would roll. Okay? And it would go out the way it came. But it would actually flip over. So it would go up here and it would be inverted. And as it's coming to right at this point here, or actually maybe right here, just where the arc starts to go backwards, it would release the bomb. Does that seem like a crazy thing to do? You're traveling almost straight up in the air and you release the bomb. What's the bomb going to do? Well, not yet. But if you're going straight up in the air when you release the bomb, okay, the bomb will go in an arc upwards, because when you release it, you've given it what? Kinetic energy, okay? And that kinetic energy, that speed, is directed upwards. So the bomb will continue to fly upwards. Because you're in a plane that's under power, you can go underneath the bomb. You can turn tighter, then the bomb will fly. The bomb is, its arc that it'll follow is fixed. Any projectile follows an arc as it flies through the air. Okay? But if you're in a plane, you can turn faster than that because you have power, you have wings, you have engines. Okay? So the plane would fly like this and then go out the way it came using gravity to accelerate it out. Meanwhile, the bomb takes longer to follow that arc and then fall onto the target, okay? Allowing the plane to release the bomb at a high altitude, avoid detection. Okay? By the time the anti-aircraft stuff is ready to fire on it, there's a problem. a thermonuclear problem. Okay, so the plane kind of gets away with throwing it over its shoulder. It's kind of just like, whoop, I didn't see it, and it just keeps going. Okay, but this is all a law of conservation of energy problem. Okay, the bomb, at its point of release, has some potential energy, and it has quite a bit of kinetic energy. Okay, when it hits the ground here, it would only have kinetic, but the amount would be a lot, but would it be the same as the sum of these two numbers? Okay, that's the principle that this thing was built on, was if you give this bomb a bunch of energy and then you allow your plane to do work on you and accelerate you faster than the bomb, you can get away before the bomb hits the ground and explodes. Okay, just using a simple physical concept, okay, but it's a practical application. It solved a, unfortunately, very practical problem at the time. Okay? Everyone kind of follow me there? So we're going to be working on problems where we would know probably the height here, and we would know the speed here, and we would be asked to calculate the speed here. Okay? Which we could do because with these two numbers and the mass of the bomb, we could calculate the initial mechanical energy of the bomb and know that here its final mechanical energy, which would be all kinetic, would be the same number. Okay? These are different from a work energy theorem problem because the energy doesn't change. Okay? The energy stays the same in these questions. What can be confusing is they appear to give you very similar information to a work energy theorem problem. You'll get two speeds, two heights. Okay? The difference here is going to be that in a work energy theorem problem, you only ever get speeds or heights. You never get both in the same question. That's only good for Science 10. You get to Physics 20 and you get both in both kinds. So in a question like this, what would I not get that I will always get in a work energy theorem question? One thing that's in work energy theorem, and I've not mentioned it once. Mass. No, I would get mass, but yeah, you're right, I haven't mentioned that. In all fairness, I did mention that, but yes, I would get mass.
It'd be force.
Yeah. I haven't mentioned force once here, have I? The only force involved in a conservation of energy question is gravity. Gravity is the only force that can 100% convert one type of energy to another. Okay? Everyone with me there? So you won't ever get a force in a question like this. That's kind of how you can tell them apart in case you ever get confused. When you're writing down your givens, because this is the challenge in physics, is, okay, here's all my givens. What kind of problem is this? Okay? It's a lot, okay? And that's a big challenge. So that's kind of what we'll be looking at here. Okay? Everyone okay with that idea? Okay? Your initial mechanical energy in a conservation of energy situation will equal your final mechanical energy. Sometimes that's as simple as the initial potential equals the final kinetic, like throwing a box off a cliff. Okay? In a question like this, I might have speed and height at the beginning, right? And I would have to calculate what just my speed would be at the end. Or maybe I have all four kinds of energy at both. Okay. All right. Now after that extinction burst, there we go. Okay. So we know that work's a change in energy. Okay, we've talked about that. But okay, the energy I get, the energy that an object has, if there's no work being done, remains the same. Okay. So things we need to remember. This is one. Okay, that mechanical energy, and we just talked about this, is the sum of an object's kinetic and potential energies. Okay, so in this first example here where we've got the baseball, it says a 0.3 kilogram baseball is thrown in a straight line through the air. Okay, what's wrong with that sentence? Yeah, well, that is part of it. Can you actually throw something like horizontally in a straight line?
No.
No. Okay. Anything you try to throw horizontally is going to arc down. It's going to fall, right? Gravity is going to ruin that for you. Okay. Nobody can throw anything in a straight line. Okay. So that's a little bit imaginary. We're just going to deal with the first instant where the person has just let the ball go. Okay. So the ball is moving is 2.50 meters above the surface of the Earth, and it has a speed of 20 meters per second. Why do questions bother telling me this?
Because then we know that we're working with 9.81 meters per second of downward acceleration.
Right. We know what gravity is. Okay. That's why they bother to say the surface of the Earth or above the Earth or whatever. Okay. So, and it has a speed of 20 meters per second. So it has height and it has speed. Does it have potential energy? Does it have kinetic energy? Okay. How do I figure out how much mechanical energy it has? Add them together, right? So all I do is just punch in my numbers here, right? I know that mechanical energy is kinetic plus potential. I know these are my two formulas because we've been using those for over a week, okay? 1/2 times 0.3 times 20 squared, that gets my kinetic energy. That's 60 joules, so most of the energy of the ball is kinetic, okay? And then 0.3 times 9.81 times the height, 2.5 meters, okay? Got 7.36 joules worth of potential energy. Add those two together and you got 67.4 joules worth of mechanical energy. Everybody okay with that? Okay. Calculating mechanical energy is pretty easy. Okay. We still have to know how to do it because it forms the basis for performing conservation of energy problems. Okay. All right. I would like you guys to try questions 8, 9, and 10 there. Okay, these are the answers here for 8, 9, and 10. Okay, these other two numbers over here we're going to talk about after. All right, so I want you guys to try 8, 9, and 10 there, and then we'll walk through them together. All right, so in the first question, the trick is obviously that it gives you the mass in grams, and it always needs to be in kilograms. Okay, so if we're calculating the mechanical energy there for that one, okay, mechanical energy will be the potential energy, so we'll have 0.3 times 9.81 times 30 meters, okay, plus 1/2 times 0.3 times 8 squared, okay, and when we punch all that in, we should get 97.89 joules worth of total mechanical energy. Okay, everybody all right with that one? Now the other two, they give you the mechanical energy. And you have to calculate either the potential or the kinetic, okay, using this formula that we were just talking about. Okay, is that going to be a pretty easy manipulation? If you're given EM, can you solve for one of the others? All right, give you a couple more minutes on those. Okay, guys, so let's have a look at number 9 here with the high jumper. Okay, so on number 9, we know that the high jumper has a mass of 55 kilograms, okay, and they're going to jump over the bar. We know that their total mechanical energy is 3.0 times 10 to the 3 joules, and we know how fast they're moving. Okay, calculate the gravitational potential energy of the athlete. All right, so I'm looking for this part of the equation. How do I get EP by itself to start with? How would I isolate EP?
Subtract dk.
Right, subtract dk over to the other side, right? I have EM, I have the mechanical energy, and because I have the speed, I'll be able to calculate their kinetic energy. What I don't have is EP. So if I take the mechanical energy and I subtract the kinetic, that should leave me with the potential if potential plus kinetic equals the other one. Okay, so the mechanical, they told me, it's 3,000 joules, okay, minus 1/2 times 55 kilograms times 8.33 squared. All right, just so you know, that's fast. That's 30 kilometers an hour. 8.33. That person is like really motoring. Okay. All right, so we've got 3,000 minus 0.5 times 55 kilograms times 8.33 squared. All right, so there's how much potential energy they have right now. Okay. Everybody follow what I did there? Okay, here's a follow-up question. This would be a part B if I was writing this question. What is the height of the bar? Okay, they're going to clear the bar. So what's the height of the bar? You just calculated their potential energy, and you know their mass. I'll give you a minute. See if you can calculate the height of the bar. Okay? Okay, so if this is their potential energy, could I say that, oh no, not again. Okay, 1091.83 joules equals M times G times H. I better be able to say that because it's true. Okay, that's their potential energy. That's how I would calculate it. Since the question told me the mass of the person, I can write on it, but I can't move it. Makes no sense. Okay. Then I should be able to take the M times G times H and divide the mg over to the other side. Agreed? Okay, I'm going to have to write up here because it's not letting me move the screen here. Okay, so I'm going to have 1091.83 divided by 55 times 9.81. So energy over mass times gravity equals the height. And when you do that, you get 2.02 meters. Okay, which is impressive. Okay? I coached track and field for 20 years. I can count on one hand the number of times I saw somebody go over 2 meters. Okay, that is an impressive jump. That is 20 centimeters over my head. Okay, that's really high. Right? Sometimes the high jump would be higher than the pole vault, because high school pole vault is high jump with a stick. It's pathetic. All right. Okay, does everyone follow how that worked? Okay, try number 3. Okay, I want you to do their question, the kinetic energy of the hammer, and then after that, I want the speed of the hammer. Okay, once you calculate the kinetic energy, I want the speed of the hammer as well, similar to what you just did. All right, so with question number 10, okay, they tell us the mechanical energy, it's 1,880 joules. Okay, they also tell us the mass of the hammer and how far above the ground the hammer is. So they've given me this number directly, and they've told me everything I need to calculate that number, and they want me to get this one. So how do I get EK by itself?
Subtract EP.
Right, subtract EP over to the other side. All right, so I'm going to have mechanical minus potential equals kinetic, and then I'm just plugging in my formulas and numbers. So 1,880 joules minus 2 times 9.81 times 50. Okay, that's going to equal EK. So when we punch all that in, right, we should get 899 joules worth of kinetic energy. All right, that's part A. Okay, if it was me making up this question, the part B would be, what is the speed of the hammer? Well, if this is EK, same as the last one, 899 joules equals 1/2 times the mass times the speed squared. So if I want to get the speed, I take the half of m and I move it over by dividing. Okay, because it's 2 kilograms. And then what do I have to do? Then I have to square root because the speed is squared. All right, so when I do that, square root of 899 divided by 1, right, should be close to 30, right? The square root of 900 should be 30, okay, meters per second. All right, those are the kinds of things we're going to be doing, but in a bit more of an involved kind of situation. This is kind of the basics of it. Okay, is everyone okay with using that mechanical energy formula? Okay, because what we're going to be doing eventually is saying the initial mechanical equals the final mechanical, right? We'll say in a situation where no work is done, the initial and final have to be the same because work is a change in energy. If no work gets done, those two things have the same number. And that's going to lead to this. EP initial plus EK initial equals EP final plus EK final. Okay? If I have to move stuff around, is it any different than what we were just doing here? Not really. Okay? If I have, all the final information and I only have enough to calculate the initial kinetic, I can bring that over here and solve for the final or the initial potential. Okay? It's exactly the same as what we were just doing, but that we're doing this right now to build up and get ready for that next step. Okay? Boy, it is finicky today. All right, so question like this. We've done questions like this as work energy theorem problems, but the purpose of this question is to tie the two ideas together. Okay, so if I pull back a bow with 100 newtons of force, half a meter, how much work have I done? 50 joules, force times distance. 100 times 0.5 is 50. Everyone okay with that? Okay, so I do 50 joules worth of work on the bow by drawing it back half a meter using 100 newtons worth of force. How much potential energy is in the bow? Did I just do work on the bow? How much work? 50. How much energy is in the bow now? 50. Okay, this is where work energy theorem and the law of conservation of energy come along, okay, or go together. On the first day of this unit, you wrote down or have in your notes the definition or the wording for the law of conservation of energy. It says, the total mechanical energy of an object or system remains the same unless work is done on the system or by the system. Okay, so work was done on the system, 50 joules worth of work. Now there are 50 joules worth of elastic potential energy in the bow. Okay, how much kinetic energy will the arrow have the instant it leaves the bow? 50 joules. That's all the energy in the system. Okay, if everything is perfect, all 50 joules of work that I did will become kinetic energy for the arrow. Okay, if I shoot the arrow straight up in the air, okay, it's going to go higher and higher, but also slower and slower, and eventually it's going to stop. When it stops, it will only have what kind of energy? Gravitational potential. How much? 50. Right. Okay? That's the idea we're trying to get at here. Okay? Once you do work and you put energy into a system, that energy doesn't change unless that system does work on something else, which is kind of what happens here. I do work on the bow. As soon as I let the bow go, does it exert a force through a distance on the arrow? Right, and it transfers all 50 joules of energy that it had to the arrow as work, mechanical energy. Okay, the arrow has kinetic energy, and then as it goes up, gravity slows it down. Okay, but it has to maintain that 50 joules worth of energy. It's going slower and slower, but it's going higher and higher. That's how it maintains that 50 joules of total mechanical energy. Okay, it doesn't all have to be kinetic all the time. They can convert into each other, and that's exactly what they do. Okay? So if my left hand, okay, is the kinetic energy as it leaves the arrow, and my right hand is the potential, okay, as the arrow goes up, okay, the kinetic goes down, right? The potential goes up, and eventually they flip-flop. At the maximum height, there's no kinetic energy because the speed is zero, and it's at its maximum height where its potential would be at its maximum. All right? That's what we're going to be working on, okay, over the next couple of days. All right. You know what? I think that's a good spot. Quit, even though there's still 5 minutes. Good spot to quit for today. All right, so tomorrow, law of conservation of energy. Okay. Also remember, your lab reports are due at 8:30 a.m. tomorrow morning, so make sure you have them done and submitted on Google Classroom.